Good morning, Astronomy 1020. Welcome to our 7th lecture. Today we have a traditional 1.5-hour lecture where we'll continue talking about the sun, and then we're going to do a lab on the rotation of the sun where we're going to track some sunspots. I want to remind you guys that next Tuesday is the midterm exam, right? Which is kind of scary. We'll talk about the format of the exam on Thursday. And on Thursday, instead of doing a traditional homework, we're going to take, well, Riordan, yeah, we'll talk about that on Thursday. It'll be a whole speech. So let me give the speech on Thursday. But let me say, just to warn you guys how important Thursday is, that on Thursday, we're going to do like a practice session for the exam. So I'm going to give you questions that are almost, actually, they're pretty much identical to the ones on the exam. I'm just going to change the numbers in the scenarios a little tiny bit. And what we'll do is, rather than me walking you through the questions one by one, you'll try to solve them on your own with me sort of staring at you, for lack of anything better to do. And then when you get into a pickle, and when you're not solving the questions, then we'll talk about it. So you can think of it as like a practice run for the exam. Obviously, that training session is like wicked important and really helpful to your success in the test. So please be there for that. That's going to be really important. I'll also go over the format and all that stuff that Riordan wants to know about then. One last announcement, but this is for mostly the Astronomy 1020 night students. In case you see this video before 6 p.m. tonight, I am going to hold a little live session at 6 p.m. tonight for night students who normally don't get live access to me. It'll be a chance for them to ask me questions, talk about whatever they want to talk about, maybe get some one-on-one help. I don't know. I don't exactly know what I'm going to do at 6 p.m., but I figured some of the night students don't get the same opportunity that you guys do to talk to me. So that's a session for them. So I'll send out an email, but if you are in the night class and you're watching this video before 6, pause it at 6 and join us. Okay, let's think about where we left off last time. We were discussing the sun, and I think one of your last notes was maybe on the layers of the sun. Is that what you guys have at the end there? Here's a picture of the layers of the sun. Christopher Leonard or Caitlin or someone who has notes, can you tell me what your last note was? Because it was a few days ago now, so I'm a little dusty on what happened there.
I have color of the sun, Wien's law, white, yellow because the atmosphere.
Wait, but is that your
solar?
Arunsak, isn't that your homework?
It might be my homework.
Oh, could you tell me about like the last lecture notes before it says homework?
Oh yeah, it's layers of the sun.
Okay, all right.
Last thing I have is hydrostatic equilibrium.
You don't have the layers of the sun in there, Christopher?
I think they're before that. Yeah.
Oh, really?
They're before that.
Wait, I did layers before hydrostatic equilibrium?
Looks like it.
Caitlin says no.
I have it like right after hydrostatic equilibrium.
Okay.
I have it.
Well,
before.
I guess as long as you both have it, someone's creative in their note taking. I don't know who it is, but that's okay. The last things we talked about, oh, someone's chiming in on the chat. I don't know if it's about that or not. Layers after. Okay, Arunsak. Today, what we're going to want to do is borrow our way from the outer edge of the sun into the core of the sun and learn a little bit about the types of energy transport processes that are happening there. So there should be a lot of cool stuff to talk about. I've got an idea. How do I want to do this? Okay, let's first have a little lesson about magnetic fields. For instance, if you guys remember, one of the most dramatic videos that I showed you guys in our first lecture was a video taken by the Solar Dynamics Observatory of the sun at X-ray wavelengths. And when you look at the sun at X-ray wavelengths, you see the outermost layer of the sun called the corona. you also see these really intense magnetic field lines that are threading their way out of the surface of the sun and up into the atmosphere of the sun. And these magnetic field lines are giving off powerful bursts of X-ray emission. Now, if I tried to put myself into your minds as best I could, you guys probably don't know what the hell a magnetic field is. And so looking at this would probably be pretty weird and confusing. Although the book doesn't do it, I thought a little mini module on what a magnetic field is might be helpful for you guys to understand the processes in the sun. And it might also help us later on when we talk about more exotic astrophysical objects. So let's start with a sort of classic picture of how a magnetic field is generated when you study these types of things in your electromagnetism course. On the left-hand side, you see a picture of a so-called bar magnet. You can literally get one of these things in the toy section at CVS. And you may know that a bar magnet has a north pole and a south pole. But the magnetic fields that are generated in a bar magnet actually have a complex microscopic origin, one that would be a little difficult to tell you at first. So let me tell you the simplest way to generate a magnetic field. It's by taking a wire, which could be, say, copper atoms, and sending a current of electricity down that wire. The current of electricity is flowing electrons that flow along the surface of the wire. And whenever charges move in a straight line, they naturally generate a magnetic field around them in the form of a circle. And in our notes, we're going to present them as rules for magnetic fields. So let's do this here together. The first rule is how we generate a magnetic field. And we would say moving charges create magnetic fields. With your permission, I'm just going to abbreviate it as M fields, if you guys are cool with that. It might not be a bad idea for you guys to draw the picture. Draw a simple copper wire. A copper wire has a bunch of copper atoms with positive nuclei. I don't know if you guys learned this in a chemistry class or what, but what makes a metal different than a non-metal in a chemistry sense is the fact that metals have an outermost electron called the valence electron, which is very loosely bound to the copper lattice itself. This electron is in a sort of casual relationship with the atom and can easily be pushed off. So I've drawn a bunch of electrons in my wire, and if I hook this wire up to the power company and I generate some electricity, if I force electrons into the wire, I can generate a flow of electrons, and that's what a current is, all right? It's a flow of electrons. As soon as the electrons begin to flow, they will generate a magnetic field. And the magnetic field, if you're sending them in a straight line, always has the same shape. It's a circular magnetic field that surrounds the wire. Wires actually generate little wimpy magnetic fields, and they can create a lot of electronic disturbance in your house. For this reason, electricians often twist wires into what's called a braided pair in the hopes that the current flowing one direction and the other will cancel out the two magnetic fields. So now we've generated a magnetic field, and I want to get you guys to think a little bit about this. What I would like to do, oh yeah, Devin's asking about the concert. Yes, it is. It is this Friday. Maybe more on that later. Okay, so here's what I want you guys to imagine. Imagine I take a wire and I hook it up to a little 3-volt battery, okay? And I take a pair of needle nose pliers, and for whatever reason, I decide to bend that wire into a little circular loop. Now what's going to happen is the current of electricity, wait, their magnetic field isn't blue, so I'll make my electricity red. The current of electricity is going to begin to flow around the wire, and the electrons will be flowing in a perfect circle. Well, almost a perfect circle. But as they're flowing around in the circle, the magnetic field will develop in this pattern with this kind of bunny ear-like shape. And when magnetic fields take these bunny ear shapes, they are known as a dipole magnetic field. And dipole magnetic fields show up all the time in nature. For instance, you may have heard in a geology class or something, or a geography class, that Earth has a dipole magnetic field with a North Pole and a South Pole. And what that suggests to me, and what that should suggest to you, is that somewhere in the hot interior of the Earth, that iron, there's a big lump of iron in the core of Earth. It must be so hot that it becomes partially ionized or plasmaified, and some of those charges must be circulating around along with the rotation of Earth. So basically you have charges that are free inside the warm molten core of the Earth, and then Earth rotates in a 24-hour period, and basically you've generated a little electromagnet. You're circulating those currents around, and you're generating a dipole magnetic field. The sun should be doing something like this, but there's a difference between the sun and the Earth. And that's the Earth has a solid, crusty, hard exterior, but the sun is not a solid ball like Earth. It is a goopy ball of rotating tapioca pudding. And because of this, the sun does not have to rotate at the same rate at all places. It's more of like a goo ball that's rotating at different rates depending on your latitude. We refer to this as differential rotation. But first, let's have a couple other rules about magnetic fields. So it's time for your second rule. Once you've generated your magnetic field, other charges that come along will either stick to, or they actually kind of orbit around magnetic fields, but it's the same as kind of sticking to them. They stick to, or they orbit around magnetic fields. In other words, if I had generated a magnetic field and then a free electron were to float through space, so here's my electron. I'll draw it kind of big so that you guys can see it on your home theater there. When my electron strikes the magnetic field, it gets captured by the magnetic field, and it goes into a little oscillation, a little planetary orbit around the magnetic field, and it gets kind of trapped by the magnetic field. This can lead to some kind of interesting effects. In the outer atmosphere of the sun, you guys will remember from my discussion with, I think, Wyatt, that the upper atmosphere of the sun is a very thin, very high temperature plasma of almost 1 million Kelvin. And at 1 million Kelvin, the electrons are basically removed from the hydrogen atoms. So you have a bunch of protons and electrons floating around. When the electrons strike the magnetic field, they're traveling at a very, very high velocity, sometimes upwards of like 70 or 80% the speed of light. And that means they have tremendously high kinetic energies. You guys may or may not remember, the kinetic energy of particles is related to the temperature. And kinetic energy basically means how fast am I going? When these high energy electrons strike the magnetic field, the magnetic field's put the brakes on the electron and they stop the electron in its tracks. I want to draw that picture one more time. Here's a magnetic field. Here is a free electron with some high kinetic energy. The electron is going to get captured by the magnetic field, and that will slow its velocity down. And then in order to conserve energy, the energy has to be transformed into the form of a very short wavelength, very high energy X-ray, so that kinetic energy gets transformed when it breaks into a very high energy X-ray photon. And this type of emission is totally different than the light generation that you learned about in your last chapter. This does not take place inside of an atom, but it's something that we call free emission. Basically, you stop an electron and you generate a photon. And the Germans refer to this type of radiation as Bremsstrahlung radiation. So let's try to write this word down. Bremsstrahlung radiation. This is kind of an esoteric physics thing. Bremsstrahlung radiation is German for braking radiation. Danke. Oh, hey, Cameron, I meant to call you yesterday, but I forgot to. Wait, there are many Camerons in this class. I don't know if you're the Cameron that usually participates or if you're another Cameron, but one of the Camerons turned in their homework and not their lab, and that was weird because normally I see you in homework and in lab. So if that's you, Cameron, oh, by the way, you know what announcement I forgot to make? How about that amnesty, huh? Who's the best professor ever? Yeah, okay, that's what I was saying. Give me some love. So look at, I think that's a really great opportunity for you guys, if you screwed up, which many of you have, to go back. You don't know about this? Yeah, okay, that's what I want to hear, Blair. Listen.
What about those of us that haven't missed any assignments? Come on, I need some credit.
Well, you can't improve upon perfection, can you, Devin? Devlin, sorry.
You can with extra credit.
In a class that's curved, there's no such thing as extra credit. There's only extra work. Stacy, do you want extra work, or are you okay with the amount of work that you already have?
No, I'm okay. Thank you, though.
I thought so.
Back it on, Professor. Back it on. I'll take it.
Because you're Star Child, that's why. All right, listen. For those of you who didn't get the memo for some reason, I'm talking to all you trolls and all you night students. Many of you have missed homeworks and labs, and I decided that if you're going to study for the test anyway by doing those homeworks and labs to encourage you to study properly, I would let you turn them in. I may take off a few points and ding you a little bit, but at least you won't be getting zeros, and that will really help some people. So I'm only doing that till the end of the week, and then I'm never doing it again because I'm going to get really screwed over by this, okay? I'm going to have hundreds of extra assignments to grade, and I know when it comes time to grade them, I'm going to regret this decision. But until then, the thing is open. So, hey, Cameron, if you were present for both, I only got one of your assignments. So go figure it out and fix that, please. Okay. I want to show you guys a little animation here using those cool physics Java apps that we've talked about before. Let's see if we can find them. S drive, physics Java apps. And I want the radiating charge. I didn't really understand this picture of radiation until I was in graduate school. So I think it's cool to show it to you. I've used this before to show you how photons are generated. Let's pretend that this charged particle is in the atmosphere of the sun, and let's give it some linear velocity that's like, I don't know, 80% the speed of light. Now, I can't show you the magnetic field. Actually, maybe I can. Can I draw a magnetic field in here? Here's a magnetic field, okay? Let's imagine this charge is traveling in the vicinity of a magnetic field, and let's just take a look what happens when it hits the magnetic field. I'll try to time this right. Boop. The magnetic field captures it, and did you guys see that little kink in the field line that happened when I put the brakes on the proton? That is your super short wavelength X-ray, okay? Let's look at that again. Ready? Boop. There you go. You can see the little emission of an X-ray. That is Bremsstrahlung radiation. Now, suppose you're thinking, I don't care about Bremsstrahlung radiation. Why are you telling me about Bremsstrahlung radiation? Because I'm trying to explain to you how, I don't know, let's see if I can find it, how this stuff happens. When you watch this video and you can see all those powerful magnetic field loops, those magnetic fields can be seen because of Bremsstrahlung radiation. You're basically seeing the X-ray emission that's coming from plasma particles hitting those magnetic field lines. So that's kind of cool. There's also one last piece to this puzzle, and now we get to our third rule for magnetic fields. Electrons can stick to magnetic fields. And in that sense, a magnetic field is kind of like flypaper, and the electrons are kind of like flies. But if you think about it, if you had a big enough wad of flies, you could stick flypaper to the flies instead of the other way around. And that's what happens with magnetic fields in the sun. Other charges stick to magnetic fields, but also magnetic field lines stick to, and they get twisted by bulk charges in the form of plasma. They stick to and they get twisted by bulk charges, which is the same thing as saying plasma. And here's where you're going to begin to understand the magnetic activity of the sun. I'm going to erase this first bit here because I need to draw a picture. The sun infamously does not have a single rotation rate, although we're going to calculate it as such today. But the sun exhibits, here's a new phrase for you guys, differential rotation. Differential rotation means the sun does not have to rotate at the same rate all across its surface. The equator of the sun actually rotates faster than the poles do. The rotation rate at the equator of the sun is 25 days, but the rotation rate at the poles is something like 35 days. So the equator is rotating faster than the poles. Let's imagine that the sun starts out with something that looks like a dipole magnetic field. That is pretty cool, right? Devin, sorry, one does not necessarily think about that beforehand, right? So imagine that the sun starts out, and imagine the sun has something that looks like that bunny ear dipole magnetic field that the Earth does. Here I want to call up a picture if I can. Just a moment. Okay. In the first slide, you can see the dipole magnetic field of the sun generated by these charges. But what's interesting and what's happening here is as the equator rotates faster than the poles, the equator starts to drag the magnetic field lines because the magnetic field lines get stuck to all of those plasma particles in the atmosphere and surface of the sun. And after 2 or 3 windings, the magnetic field of the sun becomes so wound up. It's almost like if you take a rubber band and you twist it 5 or 6 times, that the magnetic field lines start to develop a lot of magnetic tension. They become wound up, and the magnetic fields get so twisted that they end up kind of poking out of the surface of the sun in a variety of crazy ways. And you guys know what kind of cool stuff can happen then, right? What you get are solar flares. Solar flares are caused when magnetic field lines get so twisted up. I think they have one in this video here, somewhere 15 or 16 seconds in. Let's look for the solar flare that's going to happen right around my cursor here. You can see those magnetic field lines getting twisted up. Whew. Actually, this just reminds me, I have a slightly older video that might be nice to share with the class. There's an older satellite called the Trace satellite, and they kind of isolated, they have some nice pictures of solar flares. This is kind of a classic image. I'd like to show it to you. Let's open this with VLC Media Player. Okay, so this is just a few seconds long, and hopefully it doesn't stutter on your screen. I want you guys to watch this video. The Earth to scale is shown as this white disk. This is a classic image of a solar flare. Watch this. There's an eruption, and then the gravity of the sun pulls the plasma back down to the surface. So solar flares usually don't quite achieve escape velocity. They're a burst, and then gravity pulls them down. There are more energetic versions of solar flares. Those are called coronal mass ejections. And I want to show you guys a coronal mass ejection. Watch this. That's like a belch of plasma that just gets blasted off the surface of the sun. These magnetic field lines are twisting, and then poof, a huge eruption of gas gets kicked off the sun. By the way, do you guys notice that a few seconds after the eruption, you can see some static come over the CCD camera here? Obviously, because magnetic fields and plasma generate X-rays, anytime you have did I see the thing about the black holes? Yeah, actually, Devin, one of the things we're going to do in this class is talk about that stuff. So that subject is going to come up in our class again. In any case, right now you're taking your first steps into learning about how plasma, gravity, and magnetic fields interact. When you cause these eruptions, bursts of charged particles and X-rays get spit off of the sun. In any case, I want to tell you guys about something we've noticed over the years in studying the sun. The sun exhibits something called an 11-year solar magnetic cycle. An 11-year solar magnetic cycle. And that means you get something like 5.5 years of high magnetic activity. And then you get 5.5 years of low activity. Today, for instance, we are currently in a solar minimum, as it's called, and we do not see as much magnetic activity on the sun today as we did 5 years ago. And this is also deeply connected to the formation of sunspots. So I'm going to pause before I get into sunspots. But sunspots come and go along with the 7-year solar magnetic cycle. I actually sometimes take students out to look at the sun through a telescope. It is possible to do this with something called a white light filter. Can I show that to you? Oh, here. In my house, it says my internet connection is unstable, so let me know if you can't hear me. I want to show you guys something. This is just a little show and tell for fun. Do you guys see this? It looks like a piece of tin foil, right? This is called a solar white light filter. It looks like tin foil, but it's actually a shield that allows you to look at the sun with your telescope. So I put this over my telescope, and this filter only lets in 1/100,000th of the sun's light to come through. So 1 part in I think it's like, you know, it's like 0.001 of the sun. And this is enough to safely look at the sun. And it's kind of sad, guys. If you were in my class live, what I usually do around this time of year is I take the students outside and I set up the telescope while you guys sit under a tree or something. And then I show you the photosphere, the disk of the sun. And sometimes if you're in my class during a solar magnetic maximum, you get to see sunspots. Now, it so happens that I've been teaching at CCRI. Oh yeah, actually, that's true. It's rainy out. So it wouldn't have worked anyways. Good point, Devlin. But I've been teaching at CCRI for almost 10 years. So when I first started, we were approaching a solar maximum, and it was awesome because I'd take students out and they would see tons of sunspots. But just before coronavirus in the last couple years, as we entered the solar minimum, the demonstration got lamer and lamer because there were fewer sunspots to see. So maybe you can come back 5 years from now if you're still around and take a peek through my telescope. I know, Devlin, I'm getting old. Okay. Next, I want to talk about the two types of emission that the sun gives off. So the sun gives off two types of emission. And the two types of emission go like this. There is radiation, and when an astronomer says radiation, they usually mean light. But the sun also gives off particle radiation or particle emission. And here, I want to put the radiation in quotes because radiation means different types of things depending on who you're talking to. The particle radiation of the sun is called the solar wind. Okay, when I talk about radiation, when an astronomer talks about radiation, they usually mean electromagnetic waves. And that's the electromagnetic spectrum that you had to study and memorize for next week. Don't forget, students, I have a mnemonic device that'll help you remember the different zones of the electromagnetic spectrum. Gamma rays, X-rays, ultraviolet, visible, infrared, and radio. I call it YX-UVR, okay? Radiation takes the form of electromagnetic rays, which have a variety of different wavelengths. And the parameter that sums up the sun's radiation is, of course, its luminosity. The luminosity of the sun is 4 times 10 to the 26 watts. When a nuclear watchdog inspector, or when a doctor, a medical doctor, talks about radiation, they're usually talking about a different type of radiation. The sort of particle radiation that Madame Curie studied when she won her Nobel Prize in physics in the 1930s, or no, maybe even earlier than that. And when Madame Curie studied radiation, she identified 3 types of rays that she originally thought were different zones of the electromagnetic spectrum: alpha radiation, beta radiation, and gamma radiation. Through her experiments, she discovered that alpha particles were actually the nucleus of a helium atom. Okay, here's a test question. Class, what is the nucleus of a helium atom composed of? If you are a good payer attentioner, you would know the answer to that. Nucleus of a helium atom, who can tell me? Okay, Austin. Yeah, Austin. 2 protons and 2 neutrons. Son, you are ready to go. If you didn't know that, well, know it now. Let's draw a helium nucleus together. It's 2 protons and 2 neutrons. This is a very important particle in nature. It's a helium nucleus. But scientists refer to it as an alpha particle. Austin, where the hell have you been? Austin's asking, Austin, the exam is next Tuesday. Let me say this about the exam. The exam is going to be taken on Blackboard through a multiple choice test, but I think we should all log in together just like we do every day in class so that I can be available if you guys get stumped and need a hint. Does that sound like a good plan? Yeah, well, don't get too excited, Austin. It's not going to be as easy as you think. Most people do not find my exam to be an easy experience, but I will be there to help, okay? And we're going to do a practice session. Alpha particles are one of the 3 types of particle radiation that were discovered by Madame Curie. The next type, beta particles, were just a free electron. And gamma rays, this is what gets very confusing. Gamma rays are actually not particle radiation at all, but very short wavelength electromagnetic gamma ray photons. So what's really confusing about particle radiation is one of the types of particle radiation are not actually particles, but are actually the same electromagnetic rays that you find over there. This makes shit really confusing. It tends to confuse the crap out of people for obvious reasons. It's messy. When Madame Curie was studying these types of radiation, by the way, I don't know if you guys know the story, but she was studying radium and some other radioactive materials, and she ended up getting cancer and dying. She literally died for this research. Also, first woman to win a Nobel Prize, kind of cool. These types of radiation turned out to not entirely be electromagnetic radiation. These are particle radiations. Yes, she is. Now, the solar wind gives off, the sun gives off a type of particle radiation related to Madame Curie's radiation. And I need to erase this so that I can tell you about the solar wind. I also need to turn the heat down in my apartment because it's very warm. So 1 second, guys. Okay, let's talk about the solar wind. Now that presumably you understand that there's different meanings of the term radiation, the sun gives off a type of particle radiation as well as light, and it's called the solar wind. The solar wind is a stream of charged particles emitted by the sun, and it especially happens during solar flares and coronal mass ejections. Especially during so-called solar flares and the really massive eruptions that I showed you last time are known as coronal mass ejections. There are a few different particles that are emitted by the solar wind. They include protons, electrons, alpha particles, and helium ions. An example of a helium ion would be a helium atom that has lost an electron. You'll notice that neutrons are not part of the solar wind. right? Because neutrons are neutral particles. Also, neutrons cannot exist in free space for more than about 14 seconds. So this, draw an arrow, these are the particles that make up the solar wind. Sorry, Devin, are you're asking why is what? I'm not sure what your question is. Why is what? Because I just said a whole bunch of things there. Oh, this is an interesting question. Devin, it has to do with a strong force of nature, and it has to do with quarks. This is going to come up in our lecture today anyway, Devin, so let's talk about it. You might not know this, but you can actually create a neutron from smushing a proton and an electron together. They need to be coupled with a neutrino, but a proton and a neutron, when you smush them together, become a neutron. Neutrons are only stable inside the nucleus of an atom, or that's not fair to say. They're not stable for very long outside of a nucleus. 14 seconds is a short time to you and me, but to a neutron, 14 seconds is a long time. So basically, once in free space, without the compressional strong forces of the nucleus, the neutron would just rather disintegrate and separate into a proton and a neutron. We're going to talk about nuclear fusion either today or tomorrow, so you'll learn a little bit more about that eventually. Okay. Something interesting about the solar wind that you guys might not know about. From time to time, coronal mass. So let me just tell you a story here with some slideshow and some pictures. Let's get rid of this because that's going to take up bandwidth. Let's get rid of this. And I want to tell you guys a story about a coronal mass ejection, okay? Where's this bloody thing here? 42. Okay, so imagine that I'm telling you the story about how solar wind is generated, and we'll start at slide 31 here. The solar wind is constantly being pushed off of the sun, and the sun is emitting particle radiation that travels through the solar system and gets tangled up in the magnetic fields of the planets. So one day you may have this massive eruption on the sun. We call it a CME, a coronal mass ejection. And not only does plasma get blasted off the sun, but the stream of protons and electrons shoots off the sun and it travels through space. Now, these charged particles eventually make it over to Earth and they strike Earth's magnetic field. But you guys are supposed to know what happens when charged particles hit magnetic fields. They get captured by the magnetic fields. What's interesting is when the particles get captured by Earth's magnetic field, the varying field strength causes the particles to spiral along the magnetic field lines, and then it slams them into the upper atmosphere of Earth at the North Pole, and it slams some of them down into the South Pole. And you guys know what they become then, don't you? Anyone want to take a guess? They become the aurora borealis in the northern hemisphere and the aurora australis in the southern hemisphere. So those wild looking light shows that you see, the aurora borealis in the northern hemisphere, are caused by particles being emitted from the sun that get captured by Earth's magnetic field. And when they slam into the oxygen and nitrogen in our atmosphere, they generate these beautiful emission lines. If you guys go to YouTube, you can see some very, very beautiful images. YouTube aurora borealis. Some very nice videos of the aurora. Just in case you've never seen this before. So here's an evening of aurora. You have to go to very northern latitudes to see it. Okay, what if I were to ask you a test question about the aurora borealis? Class, here's the kind of question I might ask you during an exam. If I took my spectroscope and I analyzed the spectrum of the aurora borealis, what type of Kirchhoff's spectrum would I see? Do you guys know your Kirchhoff's laws? Because you're supposed to. Look how beautiful these curtains. Could you imagine if you were a primitive person watching this, you would think demons had descended from the sky. You know, it's beautiful, but also probably terrifying.
Professor, I'm sorry to interrupt you. So you cut out with the question you were going to ask
Oh,
about the, yeah, we totally missed that.
okay. So let me try it again. Thank you, Stacy. So Stacy, the question I asked is, if you took a spectroscope, remember the spectroscope that we used to analyze light spectra? If you took a spectroscope and you analyzed light from the aurora borealis, what type of Kirchhoff spectrum would you see?
Visible light.
Technically speaking, visible light is not one of the three types of spectra that Gustav Kirchhoff identified. Visible light, Austin, if that was you, is a band of the electromagnetic spectrum. But Austin, to answer this question, you need to first know the three types of spectra identified by Gustav Kirchhoff. Can someone start off?
I have to find it.
Yeah, why don't you guys find that and look it up first? I'm asking you this question because I'm guessing most of you do not know the answer to it. Paul G does, however. Paul G, you are the man. Paul G has correctly identified the type of spectrum as an emission spectrum. Okay, first of all, Austin, did you find the three types of spectra identified by Kirchhoff?
No, I let Paul G do all the work.
Well, we still need to understand. I suspect most of you don't even understand the answer to that question, and that worries me. So let's figure it out right now together. Tell me, someone in this class, what are the three types of spectra recognized by Kirchhoff? Cameron says continuous, that is one type. Obviously, emission is another type, and then absorption, correct. Thank you, Cameron and Paul G. Emission, absorption, and continuous spectra. Okay, now Paul G, if you want to type it up or if someone else can explain, why is it emission? How does Paul G know it's emission? Can someone out there explain that to me? How does he know this is an emission line spectrum?
Is it because it's produced by a hot, thin gas?
That's exactly the correct answer. Up in the upper atmosphere, it's a hot, thin gas. And in fact, do you guys see the green colors, the green curtains of light? I happen to know that they're caused from the 4 to 3 transition of ionized oxygen. I don't know what the red ones are caused by. However, sometimes you've got to be careful. I want to show you something else. I want to see if I can do a demo for you guys. Hey, Paul G, what type of spectrum do you think this is if you analyze it with a spectroscope? What type of spectrum would that be?
Continuous?
Very good, Austin. How did you know? Yeah, Paul G, it would not be emission. Actually,
Yeah,
Austin's
Paul,
got
late
you.
on that one.
Okay, but how did you know that, Austin? Was it a
Well,
guess? Or...
I just thought that there was a continuous flow of like butane or
No.
like. So
I want
know,
to talk to Paul G.
not-
I want to talk to Paul G again. Why would Paul G assume this was an emission spectrum? That's what he suggested. First of all, let's see if we can actually do it. Can I perform this experiment? This is going to require some very deft handling. Hold on a second. I did this the other day somehow. I've got to get the angle just right. Ah, gosh. No, I can't tape it to the camera. That's not going to work. This thing is really long. I had it for, oh, there we go. Did you guys see that it was continue? All right, you only saw it for a second. No, you can't, that's not gonna work. Okay, I ain't gonna explain that. You guys just saw it for a hot second there. You could see that it was a perfect rainbow. It was not an emission line spectrum. Why is it not emission? Why is it continuous? This is really important to understand the sun.
Well, my notes say that they come from a hot, dense solid.
Exactly,
Well,
which is kind of, but it's there's no solid there, Arunsak.
That's what I was thinking. How is a lighter a dense solid?
Exactly. And can I tell you something? This is a confusion that I had as well. When I was a student, if you had asked me that question, I would have said, according to Kirchhoff, a gas produces an emission spectrum, so that's got to be an emission spectrum. And why I would be wrong, Arunsak, is I was taking Kirchhoff too literally, and I was assuming that anytime you have a gas, it has to produce an emission spectrum. The problem, Arunsak, is the density of air in this room is actually so high that the packed together air molecules, when they heat up, actually glow just like a piece of steel in a forge. The type of gases that produce emission spectrum are very, very low density. They have densities of millions of times less than the air in this room. That's why when I showed you emission line spectrum, I had to have tubes of gas that were extremely low density helium or mercury or something like that. I couldn't just do it with air in this room. So I guess what I'm trying to get you to understand, Arunsak and friends, is even air, when you heat it up, actually acts like a dense solid more than it does like a thin gas. The density of air in this room is quite dense. And it is for this reason that the surface of our sun, the photosphere, actually glows as a black body. The photosphere of the sun actually has lower density than the air in this room, but for all intents and purposes, yes, Christopher Leonard, that's why I called it a hot, dense thingy, because I was anticipating the fact that I had to tell you something confusing in the future, which is that the surface of the sun is a gas, but it also is a black body. So correct.
Wait, Professor, but the definition says a dense solid.
I know.
You call the air a solid?
Yeah. Can I tell you something
And
about Arunsak? I'm going to tell you an important truth about laws of physics. In physics, in science, something is only elevated to the status of law once it's proven false. And most of the basic things that you're taught in science are actually lies. But the reason we start off telling you lies is because you can't handle the truth. You have to build your way up towards the truth by learning a whole bunch of lies. And Kirchhoff saying hot, dense, solid is a lie because it's simple, and people tend to understand simple things and not complicated ones. But the truth is complicated. And welcome to life, kiddo. Okay. All right. Anyways, let's do a tidbit on the layers of the sun. Yes, I get paid to lie in particular, which is really funny and ironic. Let's go and dive into the layers of the sun and learn a little bit more about them. Okay, so I want to start on the outside. I want to talk about, let's see here. What are my best image of the layers of the sun? This picture, I don't know where I got it, but it shows the solar wind. It shows the corona, the chromosphere. Let's just kind of do a little tidbit on all the layers of the sun. And I want to try some math problems with you guys. This is also going to be training for the types of questions you can expect on the exam, okay? Okay. Let's talk about the outer layers of the sun. They include the corona, and the chromosphere. The big difference between these two layers is their temperature. The corona has a temperature of 1,000,000 Kelvin. The chromosphere has a temperature of 10,000 Kelvin. The temperatures actually vary a bit, but those are representative numbers. Both layers are low density high temperature plasmas that surround the sun. To give you an example of how low density some of these gases are, I could literally, if I took a bucket full of 1,000,000 Kelvin plasma corona and I filled your apartment with it, you would not be burned or harmed in any way because the density of the plasma, yeah, I will, Cameron, the density of the plasma is so low that there is not enough heat inside the particles to actually cause you to be burned. So the corona is a very, very wispy, tenuous layer of the sun, but it's at extremely high temperatures. Both layers, you know, it's kind of weird that these layers would be hotter than the photosphere because they're closer to the outer vacuum of space. Normally, one would think the closer you get to the edge of space, the colder you should get. The reason why these layers are so hot is because of all of those twisting magnetic field lines that you saw in those videos that I showed today. As the magnetic fields twist and turn around, they become kind of like an egg beater that spins up and heats up the plasma. So these layers are heated by twisting magnetic fields and what we might call solar storms. Here's a key idea. These two layers radiate at different principal wavelengths. They give off different peak wavelengths of emission. Do you guys remember the formula that lets you calculate the peak wavelength of emission based on the temperature of a material? Please take these notes down because I'm going to have to erase them in a second. Okay, I'm erasing this. Here's a question for the class. This is a question I could easily ask you during the exam. Christopher?
You said max wavelength,
Yes.
Wien's law.
Very good, Christopher. Excellent job. Find the peak wavelength emitted by the corona and the chromosphere. I should mention that normally Wien's law is used for black bodies, but these things are so high temperature that it kind of doesn't matter. So let's use Wien's law. The peak wavelength of emission is 3 million nanometer kelvins divided by the temperature. So first we'll start with the corona. Lambda max is 3 million nanometer kelvins divided by 1 million Kelvin. What's that work out to be?
Three nanometers.
Now, for the follow-up question that I will most definitely ask during the exam. In what region of the electromagnetic spectrum is 3 nanometer light found? If you have trouble with this, remember I have a slideshow. Oh, where is it?
X-ray.
Very good. I just want to show you guys how Christopher got that. Notice
I
that
got
the
it from my notes.
good. Okay, this is also a slide that you could use, Christopher. This is your electromagnetic spectrum. 3 nanometers would be right about there, right? The cutoff is 10 nanometers. Let's now do it for the chromosphere. So this is X-ray light. Make sure you write that down. Chromosphere. Divided by 10,000 Kelvin. What do you get?
$300 nanometers.
Okay, Christopher, since you got the last one, let me make sure that there's somebody else besides you who understands how to do this. Can someone besides Christopher tell me what regime of the electromagnetic spectrum 300 nanometer light is found?
Ultraviolet.
Excellent. Okay. For this reason, folks, the only real way to see the chromosphere is to look at the sun in ultraviolet wavelengths. Let's do that. So weirdly, the first picture that I have of the corona is actually in visible light. The corona might give off principally X-rays, but it's so bloody hot that it actually glows at visible wavelengths as well. So there's a picture of the corona in visible light seen during an eclipse. Notice that the wispy corona extends many solar radii out, but that it's not uniform. It's kind of patchy and wispy. Here's an ultraviolet image of the chromosphere. Notice that even the chromosphere is not a uniformly smooth layer, but it kind of looks like a dog with the mange, okay? It's got like these patches, and they call those patches coronal holes. So the chromosphere is also a turbulent and wispy layer. You can actually kind of see those magnetic field lines that are heating it up. By the time you get down to the next layer of the sun, the photosphere, you'll notice that it's no longer wispy or patchy, but the photosphere has a very, very uniform illumination with the exception of sunspots. That's because we're generating light at this layer by a different process. Let's talk about it. I'm erasing here. Let's talk about the photosphere a lot. The photosphere is kind of like the surface of the sun. But it's not a surface in a physical sense because it's actually made of a thin gas. Well, sorry, it's actually made of a gas that I don't want to call thin, a gas that is similar to the density of air in this room. The photosphere is literally the coolest layer of the sun. It has a key temperature of 5,800 Kelvin. I could define the photosphere in this way. That layer that produces visible light. So we define the photosphere as whatever layer of gas is producing visible light. It produces this light by thermal blackbody radiation. You guys may want to remember the phrase that I came up with for thermal blackbody radiation. I glow because I'm hot. Because I wouldn't say it's an insulator, Devin, because well, air is actually a good insulator and the density of gas is similar to air, but you're thinking about it the wrong way. You're thinking of an insulator as something that prevents heat from flowing from one place to another. Like if you have insulation in your home, you're trying to prevent conduction from transmitting heat from the interior of your house to the exterior. The photosphere of the sun is actually transmitting energy out of the sun into space through radiation. So it's not acting like an insulator, it's acting like an energy transmitter. It's transmitting energy from the interior of the sun to the exterior. I would not say that it's an insulator in any way. For instance, the layer of the photosphere is incredibly thin. It's only 50 kilometers thin in comparison to the radius of the sun. The radius of the sun is 700,000 kilometers. So let's try to imagine what that would be like. Okay, so here's the sun. And Devin, this is kind of related to your question. Let's say the radius of the sun is 700,000 kilometers, but the thickness here is only 50 kilometers. Now, Devin, what's happening is the gas up here is too thin and too hot to generate visible light. Down here, the gas is thick enough and hot enough to generate visible light, but light cannot escape the interior layers because the density of gas is so thick that the photons become reabsorbed. So there are photons jiggling around down here, but the photons are getting absorbed by other atoms. Only once you get to the perfect medium thinness of the photosphere can the photons actually escape the space, which is why these layers are insulated by their own thickness, but the photosphere is actually transmitting energy to space through radiation. I'd like you guys to consider what percentage of the sun's radius 50 kilometers is. Can you guys work that out for me? What is 50 kilometers divided by 700,000 kilometers? Punch that up for me. Hold on, Arunsak. I suspect you did that wrong. Well, I think you just, hold on. 50 divided by 700,000. Okay, Arunsak, this is the number that I got too, but that's not the same as the percentage, Arunsak, right? You got to know how to translate from decimal to percentage. So you get 0.00007, but Arunsak, that is not 7 times 10 to the minus 5%. That's just 7 times 10 to the minus 5. How do I convert that into a percent, class?
You move the decimal like forward 2 places.
Correct. And Austin has also gotten it here. 0.007%. Could you guys think of a good analogy for the sun? The photosphere of the sun would be comparable to what? Well, no, this is kind of a nasty onion. I probably should have used this a while ago. Let's consider a yellow onion. And I want you guys to, I wish I had a nicer one, but it's time to throw this thing out. Consider the paper skin, that thin little wax paper that you get at the edge of an onion. What would you say the diameter of an onion is? Let's take out my ruler here. The diameter of this onion is, nice, Austin, is 10 centimeters. So I'm going to erase up here. Let's compare the sun to an onion. So my onion has a diameter of 10 centimeters. Meaning the radius is 5 centimeters. What about the thickness of onion skin? Does anyone have an idea of how you might measure that? It is clearly less than a millimeter. Okay, Austin, give me a guess.
I don't know, half of a millimeter.
No, it's clearly thinner than that. Here's the way that I did it. This is a better demo in person than my camera doesn't like it when I zoom too close. Well, unless I open up that thing and do a big thing. Listen, no, not a few nanometers. You can see the thickness of an onion. You cannot see it. Nanometers is too thin. The way I did it is I took pieces of paper. I assumed that paper was close to the thinness of an onion skin. And I stacked up pieces of paper until I filled up 1 little millimeter. And when I counted the number of sheets of paper to do that, it was close to 10. That tells me that onion skin is probably close to 1/10 of a millimeter. So the skin of an onion okay. What percentage of an onion does the skin comprise? Can you guys tell me? No, no, no. Everyone who's chatting me right now is getting it wrong. How do I do this? Oh, no, Paul G. You have the number right, but your units are wrong. How many centimeters is 0.1 millimeters? You got to convert that to centimeters first. That's the trick. Someone talk to me here, please. Please, for the love of God, tell me you know what a millimeter is. If you don't know what millimeters and centimeters are, then I'm seriously concerned for your well-being.
Is it 1/1000th of a centimeter?
All right, I'm going to have to get out my Logitech so I can zoom here. Jeez Louise. No. All right. Where's my ruler? Hold on, my Logitech is opening so I can zoom here. Okay. Look. Do you guys, I need a white background. Let me get a cue card here. Okay. Which ones are the centimeters and which ones are the millimeters?
So the small ticks, the smaller ones are 1 millimeter, and then your big ticks are 1 cm. So it's 1/10.
1/10. Okay, great. So exactly. That's why I'm saying all you have to do is look at a ruler and you know what the answer is. So Arunsak, 0.1 millimeters is how many centimeters? Come,
It's 0.01.
thank you. Jesus Christ. Okay. 0.01 centimeters, okay? 0.01 centimeters divided by 5 centimeters. And Paul, the centimeters cancel out. That was my complaint with your answer. What do I get? Very good, Christopher. I get 0.002 or 0.2%. Guys, put a box around this number and put a box around this number. I'm trying to make a point here, but you kind of need to have ears to understand the point. What's my point? Does anyone understand what I'm trying to say?
Yeah, the photosphere is super thin compared to the radius of the sun.
Yes, Arunsak, that's the first blush. How many times thinner than an onion to scale? How many times thinner than this stuff? I think this
About 100 or 1,000 times.
divide 0.2 by 0.007.
$29 times.
About 30 times. "30 times thinner than the skin of an onion." That's the point that I'm trying to make. In fact, there's something about that result that I think is interesting. If you guys look at a picture of the sun, this explains why the edge of the sun is so crispy sharp. The sun is not a planet like Earth. It's a ball of gas. Balls of gas aren't supposed to look really sharp and well-defined. The edge of the sun is as sharp as the edge of a razor because the layer that's producing the visible light is so hyper thin, 30 times thinner than a skin of an onion to scale, that it's almost like a candy-coated surface that's producing the visible light. And the solid temperature is what makes the uniform illumination look so intense. Actually, you guys can see that it looks a little bit darker at the edge of the sun. That's called limb darkening. That's because when you slice through the edge of the sun, you're not cutting as deep into the photosphere as when you cut through the center. So it's a little brighter towards the middle and a little darker towards the edge. But this lesson that we just did about onion skin is trying to explain to you why the edge of the sun looks so crispy sharp when you see it with your naked eye. There's a few other things of interest to mention about the photosphere. First of all, we find sunspots on the photosphere. Let's write that down as well. Yeah, the sun is kind of like an M&M. let's do more on the photosphere. Okay. First thing I got to mention is that sunspots are found in the photosphere. What is the cause of sunspots? They are regions of cooler plasma that are trapped by magnetic fields. That are trapped by magnetic fields. So here's a picture of how this works. You have the photosphere. Now I'm going to zoom in on the photosphere. And we have powerful magnetic field lines threading their way through the sun. So here's our big magnetic field loop. Remember that magnetic fields trap plasma. So what happens is the plasma that gets trapped near the base of the magnetic field lines becomes colder than the surrounding plasma, and the sunspots appear darker by contrast. They usually come in pairs. There's a north and a south pole for every sunspot. And they usually vary with an 11-year solar magnetic cycle. So they vary the number of sunspots with the 11-year solar cycle. Typically, the temperature of a sunspot is something around 3,500 Kelvin or maybe 4,000 Kelvin. And in our next class, we'll do a sample problem on that. So I want you guys to remember that we did this. I just realized it's 1 o'clock and it'll be time for our lab soon. Would you guys like to stop and take a little break here before we start our lab today? Tracking sunspots? Okay. All right, I think that's a great idea. So let's take 10 or 15 minutes and then we'll get back to it. I'm going to pause. Okay, students, welcome to our lab on the rotation of the sun. Probably most of you guys are not going to have the right materials, but let's start with what you might have. I've got a few printouts here. Let me see if I can find one without the suns. All right. So the pages that we would like to work with sorry, I'm getting organized here. This page shows you several images of the sun along with key photographs of sunspots. We have our sunspot tracking page 13.5, and then we have our analysis page 13.6. Also, the thing that you guys probably won't have, but you can use a regular piece of paper, although it's not as good. What we would like ideally is a piece of tracing paper, and we're going to make a model of the sun and track some sunspots across it. If you don't have tracing paper, just cut another piece of paper. The rough dimensions should be about 10 centimeters by 10 centimeters, something like that. I have some scissors here, so I'll make those cuts now. Doesn't have to be perfect. We'll just there we go. So I've cut a piece of paper that's about 10 centimeters by 10 centimeters. I actually have tracing paper, but you guys You guys may not have that. A regular piece of paper you might be able to see through it as well. Won't be quite as good as tracing paper, but so what? Okay, the goal is for us to calculate the rotation of the sun by tracking a number of sunspots across the face of the sun. Now, what we would like to do is get the equatorial rotation rate of the sun. Does anyone have a good enough memory that they know roughly what we should be expecting? What's the rotation rate of the sun along the equator?
Wasn't it like 25 days?
Excellent, Arunsak. Yes. So my idea is that if we track sunspots somewhere in the northern hemisphere, and then track a second sunspot somewhere in the southern hemisphere, if we average the two, it should give us the rotation rate along the equator. So we're hoping to get something around 25 days. Let me get my cell phone out, and let's see if I can connect to the Zoom through wireless here. This is always fraught with difficulties, so. Okay, I'm going to attempt to share screen. Come on, to the iPhone. I can't believe it. It wants the plugin to be installed every time. It's so confusing. Okay. Oh, sorry. That's not what was supposed to come up. Oh, this is really annoying. Oh, Jesus Christ. Okay, hold on a second. Apparently, my storage is full, and that means I'm going to have to delete a video or two, which makes me very sad. Damn it. Sorry, guys. Apparently, I can't even activate the camera until I delete a few more videos. Oh, this is really sad. Very, very irritating. All right, let's try this again. Oh, thank God. All right, crisis averted. Let's go to our first page, which is 13-5. And I'm going to unplug this for a moment and put it inside the tape. Let's get my pencil out. Go. And first thing we'd like to do is get our name on this page. This is lab number 7. And our section is astronomy 1020. Don't forget to put your lab section after whatever it is, 001, 002. If you're in the night class, you can put 101. Okay. Let me reduce the intensity of it. Okay. We first want to go to our sun. And at the very first sun, we're going to try to measure the diameter. Whenever you measure the diameter of an astronomical object, you always want to do it vertically because sometimes astronomical objects can bulge along their equators. So what would you guys say? Can you read this in centimeters, or let's do it in millimeters? What would you say is the diameter of the sun? Let me hold the phone up here.
Like 54 millimeters.
Good. So what would that make the radius of the sun on our page if we divide that by 2? What's half of 54?
27 millimeters.
Okay, so I'm going to take this here compass, and I'm going to use the compass to make a circle that is 26 millimeters in radius. And here's how I'm going to do that, Arunsak. I'm going to, ooh, my phone is warm. I'm going to take this ruler, and I'm going to make tick marks at 0 and at 26 millimeters up here. So I'll make a tick mark kind of vertically up. This is how carpenters do it. At 0 and 1 at 26. And that's what I should set the radius of my compass to. I don't know if you guys have a compass, but if you did, that would be kind of dope. Otherwise, you're going to have to flub it. Maybe you could take your tracing paper and trace over the sun, which will be less good. So I'm setting mine here at about the 26. Okay. Now what I'm going to do is I'm going to make a little model of the sun that's 26 millimeters in radius. So I'm just going to put the sun onto a piece of paper here. And somewhere in the middle, I'll spike it, and then you pin it and spin it, okay? You pin it down and you kind of spin around gracefully. Going over it a few times to make it nice and dark. Before we proceed, we need to make sure that my model of the sun actually matches the one on the page. So I'll take a minute to kind of put it over, and it should be good to within a millimeter. Mine's about right. I wish I had made it even a teensy bit bigger. But I think that's good enough. We'll see if it's good enough anyways. Before we proceed, we need to make some reference tick marks, okay? The reference tick marks are there so that you don't accidentally twist this thing around. Man, I'm a little unhappy. Can you see how there's just like a little bit on the edge here? That's bothering me.
Did you do 26? It was 20. It was 27. That's why.
Oh,
Yeah.
wait, it was 54, right? Half of
Yep.
50
54 divided by 2 is 27.
Well, Arunsak, that explains why I'm a big dummy today, doesn't it? All right,
Mhm.
let's try that again. That's easy enough to fix. Thank you. Probably should have used a calculator for that. All right, let's try that again. Let's take my ruler, and this time let's do 27. So I'll make a tick there and a tick at 27. Thank you, Arunsak, for keeping me on my toes here. Okay. I gotta make sure this stays flat. I keep poking it. Yeah, okay. And here I am making my circle. That was really boneheaded of me. Thank you very much for catching that. Okay, let's hold it over. This paper is a little more wrinkly, but at least my circle is more satisfying now. Can you guys see that? This requires very precise measurements. So if you're sloppy, your results come out sloppy. So I think it was worthwhile, Arunsak, to correct that. Okay, now what we're going to do is you can see there are these tick marks, north, south, east, and west. And I am going to very carefully trace those tick marks, north, east, south, and west. And I call these the registration tick marks. The registration tick marks, this is north, and I believe, oh, sorry, north is on the bottom, and east is on the right. Wow, okay. So north is on the bottom, and east is on the right. You guys will remember that telescopes actually invert everything. So since these measurements were taken through a telescope, north is on the bottom. Okay. Sorry, my phone is crapping out here. I gotta plug it in. Now, we have to pick the sunspots that we want to track. My idea is that we should pick this really dark spot. You can see it kind of moving across the southern hemisphere here. So this spot, oh, I'm upside down. Let's try that again. You guys can see here that the darkest spot is on the third day is this one. And that dark spot is the one that I'm going to want to track. So if it's not present on the first day, but I think it shows up on the second day right about here. So we're going to track that spot. That's on 7/27. We're only going to track one of the darker spots. On 7/30, it's this one. On 8/1, it slides over to here. Excuse me. 8/3, it's the dark spot that you see there. And 8/6, it's at the edge. That's one of the spots we're going to track. We're also going to track one that's in the, so that was in the, well, technically the northern hemisphere, right? We're also going to track one in the southern hemisphere. That spot becomes that spot, becomes that spot. On 8/14, it's this one. On 8/16, it's that one. And on 8/18, it's right at the edge. Okay, the very first day, 7/25 has no spot of it. Well, it has spots, but we're not going to track any of them. So the very first observation is on 7/27. Now I want you to watch how I do this. I'm going to try to, hopefully I can hold this in with the tape. First, I'm going to place the registration tick marks carefully over their respective spots. And I'm going to fill in my spot, trace over it. And then I'm going to label it with the date underneath as a month/day. So that's 7/27. And I'll put that right there. Sorry, I know it's a little faded and kind of hard to see. Next, we'll go to our next date. Track the spot there. And that date is 7/30. So I'm going to neatly write underneath the spot 7/30. Make sure your pencil is nice and sharp for this. Make sure you match your registration tick marks every time before you track the spot. That spot there is 8-1. On our next observation day, let's line up the tick marks. We'll go there. That's 8-3. And then carefully line up your registration tick marks each time. There's my last spot. And that's 8-6. So currently my doodah looks something like this. And that's what your doodah should look like too. Okay. This is going to be one of the spots. We'll call this the B. Let's see. Yeah, this will be the B spot. And we'll do an A spot in the southern hemisphere. The southern hemisphere being the one that's above. So on the first date, well, yeah, it's 8-8. My spot is right here. 8-8. Next, we'll track a spot going here. That's 8-10. I have to write really tiny. My next spot is here. That's 8-12. You guys following this okay? All right. Now we're going to 8-14. We're going to track that spot. Match up my registration tick marks. That's 8-14. I'll go here. Shade in that spot. That is 8-16. And then one last spot. And that's 8-18. Okay. When all's said and done, we've got, whoops, something that looks like this. All right. So let me try to explain what we're going to do next. You might naively think, well, can I just wait until the sunspot comes around again? And that's how I'll track the sunspot. Once the sunspot disappears behind the limb of the sun, you lose track of it and you won't be sure what sunspot it is when it comes around again, because they often kind of mutate and shapeshift a little bit. What we're going to need to do is track a sunspot through a fraction of its rotation and see if we can like predict how long it will take to go around the sun. Oh, you bastard. What? It was working? Oh my gosh. No, I don't want to deal with this. Okay, Jesus Christ. Okay. Sorry. I need to make sure that my phone is old, so it can't handle things. If I delete some more pictures, hopefully it'll. Okay, that seems to have worked. Share screen, iPhone. Wow, I'm having good luck with this thing today. Bad luck with my phone, but good luck with this. Okay, so what we're going to do is we are going to draw a best fit line that goes through the middle of these points. And we want to make sure that the line stays horizontal. So watch how I do this. I'm taking my ruler, and you can see the sunspots kind of have a little bit of a smile shape to them. I want to keep it kind of horizontal, but I want to go through the middle of the spots. So I get kind of equal numbers above, below, and on the line. I think this is pretty good. Let's try it. Notice that best fit line. Well, probably could have even been a little better fit, but I've got a few more spots below than I do above, but I'm just going to go with it. Let's try to do that here. This time I'll really make sure that I've got equal numbers above and below. Okay, notice my best fit line only extends to the edge of the sun. What we're going to do is we're going to imagine cutting through the sun at these latitudes, and we're going to try to project the sunspots to the surface of the sun so we can calculate their angular rotation rate. I want to know how many degrees per day does a spot rotate across the face of the sun. So what we're going to do is we're going to transfer lines of exactly these lengths near spot A and near spot B on page 13-5. So let's do the first measurement together. This is our A spot up here, and our B spot is down there. Let's measure the length of the line for the A spot. So Arunsak, you seem to be pretty good at measurement, better than me today anyways. What would you say the length of that line is?
It looks like 52, 53, 53.
I think it's a little close. The inside is a little closer to 52. So let's go with that. Okay. So this line is 52 centimeters. Now watch where I make this line. You've got to make it in exactly the same place. Right next to where it says spot A, make your line just to the right of that and make a line that's exactly 52 millimeters, but no more. So Runsack, let's divide 52 by 2. I think that's 26, right? Okay, all right. So let's make a line at the midpoint, right? Oops. Oh, geez. So this is 52, and I'm going to make a line right at 26. I don't want it to look like a spot, so I'm going to make it kind of like a vertical tick mark. The reason I'm doing this is this line is a slice through the sun, and I want to use my compass to draw the belly of the sun. I want to draw the projection of the sun so that I can see where the sunspots are rotating. So what I'll do is I'll take my compass, and I'll make sure I set my compass now to 26. Bring it in a little bit. 26 millimeters. And I'm just, oh, fudge. It really helps to trust me on this. If you have a compass, put it underneath some padding, or you won't get a good semicircle. I should probably go a little slower and let you guys catch up. Are you guys managing this at all? Kind of. Arunsak's got it. Let me sip some seltzer while you guys work on that. Caitlin, are you managing to do something like this? Oh, okay, cool. How are you doing, Stacy? Good. Oh, awesome. Okay, I love it. Let's do the same thing for the B spot while we're at it. Let's measure the length of the B spot line. It looks like I'm getting just about 50 millimeters. Hold on. It could be 49 or it could be 50, but let's go with 50 for the hell of it. Make sure you put this right next to where it says spot B. That's very important. Okay, I gotta get rid of the padding for a second. There's a reason why I want to put this, okay, from 0 to 50. And mark the midpoint while you're at it. The midpoint is 25. Make a tick mark right at 25. And then we're going to draw in, oh, shoot. So this line is 50 millimeters with a hash mark at 25. Let's get some padding underneath that. Let's draw in a radius at that point. Probably should have sharpened up my compass there. That line is a little bit thick. You can see I stabbed it a little off. I did kind of a shitty job there. Okay. What we need to do now is we want to project the sunspots onto the line and then try to project them up to the surface of the sun so we can see what kind of an angular rate they're rotating through. And there's kind of a quick and fun way to do this. What I'm going to do, and what you can do too if you have some kind of a tracing paper or whatever, is I'm going to slide. You know, I probably should have made a photocopy of this. That would have been nice, but whatever. I'm going to slide this over the tracing paper. I'm sorry. I'm going to slide the tracing paper over my line. And I'm going to take the compass and I'm going to kind of poke through and make divots wherever there's a sunspot. So let me put this inside the tape roll so you can see what I'm doing here. Put this over, and then I'm just going to poke through with the pointy part of my compass to make some divots. So I'll go dink, dink. Get the fuck out of here. All right. Dink. Notice that I'm forcing the spots to be on the line, even they're a little below it or above it. Dink. 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 All right, that's more efficient than measuring. So I just poked with the pointy edge of my compass through these spots. And now you can see I've got a bunch of divots in the line. and I can fill them in with my pencil, make them a little darker. And then I'm going to put the dates underneath each of the spots. By the way, this is how people actually measured the rotation of the sun originally. So this is a very legendary lab. So I've got 8-8, 8-10, 8-12, 8-14, 8-16, 8-18. That's easy to remember. 8-8, 8-10, 8-12, 8-14, 8-16, 8-18. So I'm just transferring the dates to the spots. Give you a second to catch up to that. Okay. Let's do the same thing for the B spot now. I was just kind of giving you guys a moment to catch up to me. So we'll put the B line down here. Notice that it matches up with the length of the line that I drew before. And once again, I'm going to poke through using the pointy part of my compass, and I'm going to make divots at each spot. Dink, 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 dink. I'm forcing the spots to be on the line. Okay. We've got 727, 730. 8-1, 8-3, and 8-6. All right, so this is what you should have at this point. Let me just sip some seltzers to let the daytime students catch up since they can't pause it.
Professor, I'm freehanding everything, but it looks pretty decent.
Okay,
Just so you know.
I like it, Arunsak. You do the best you can. I know it's. Can I see? Yeah, okay. It would have been nice if you could have found a circle maker, but all right.
I don't have one of those circle Mickeys.
You know, this thing costs like $2 at Job Lot. So if you're at Job Lot or if you're out a supermarket or something in the next week or so, just grab one of these. Cheap, cheap. Actually, the number of times we're going to need them is pretty limited. So, okay. What we want to do now, all right, so I need you guys to hear me out about how this works. So let me show you another type of circle maker. This one's a little quicker than a compass, but But hear me out on this, okay? To measure the rotation, to measure the rotation period of the sun, we would like to know, like, how long does it take a sunspot to go around the sun? So for instance, if there was a sunspot here, right, the period of the sun's rotation would be the time that it takes to go all the way around the sun. And that would be a sort of 360-degree spin of a spot. But we're not going to be able to track the spot throughout a complete rotation of the sun. We're going to pick 2 dates, and we're going to try to figure out how many degrees theta does the sunspot rotate in how many days. And what we'll do is we'll calculate something called the angular velocity. The angular velocity is some number of degrees per day that your sunspot rotates. So for instance, if I rotate, theta degrees, it could be 10 or 12 degrees in 12 days, then we'll say that that rotation rate is equal to 360 degrees in some unknown period worth of days. And then we can kind of solve for the period using algebra and say that the period is 360 degrees over basically the angular velocity. Because the angular velocity are your degrees per day. So this is equal to your angular velocity. Okay, so what I want to do is, with that in mind, I want to track 2 of my sunspots up to the surface of the sun. I can pick any 2 I want, but the goal is to pick ones that are either side of the center. I don't want them to be too close to the edge. I like to go with this sunspot and this sunspot, and I want you to watch how I do this. I'm going to take my ruler and I'm going to just track them up to the surface of the sun. I'm going to make sure it's kind of vertical. I want it to be really vertical. I'm going to track that spot up to the surface, 810, and I'll track this spot, 816, up to the surface as well. Now what I'm going to do is I'm going to make a line that goes from the center of the sun up through the intersection where the spot intersects with the surface. This is how I'm going to measure the angle. So put your pencil on the center and put your ruler over there and drag that line way the hell out, like really, really far on both sides. Let's do the same thing down here for one of these spots. I'll pick 730 and 83. Notice I go up to the surface, but no farther. Notice that I like to use one of these tick mark lines to help make sure that I'm perpendicular. Okay, now I'm going to sort of make an angle here from the center way up through the intersection like that. And way up to the intersection like that. Extend those lines really, really far. These are a little crooked, but okay. Not too crooked. Next job is for us to try to measure this angle. To measure an angle, use one of these bad boys. If you can see my window here, it's a protractor. And what you do is you take your protractor and you put the hole there at the vertex of the angle. Then you pin pin it with your pencil and you spin and you rotate until 0 degrees up here lines up with one of your arms. Now, I know this angle is less than 90 degrees. So what would you guys say the angle is?
74.
Okay. So we'll write that down here in the elbow. 74 degrees. Let's do it for our B spot as well. You pin it and you spin it. You put the vertex at the hole, okay? You pin with your pencil and you spin on, oops, sorry. You pin with your pencil until 0 degrees lines up with one of your arms. Then we measure our angle. Looks like 55 to me. Okay. So what is the, we have to get the time interval for starters. What is the time interval between this spot and this spot? How many days?
Is it 6 days?
Yeah. And to calculate our angular velocity, we have to divide degrees, by days. So that's 74 degrees divided by 6 days. We're going to keep 3 sig figs for now. That's 12.3 degrees per day. All right. How many days are between these two sunspots for spot B? This is July and this is August. How many days are in
3.
July?
4 days. The total interval, 4 days.
Caitlin, you're saying the total interval is 4 days?
Yeah.
Very good. Let's just see how Caitlin did that. 31st to the 1st to the 2nd to the 3rd. I can't really do that. Is 4 days. Okay. Very good. Now let's calculate our angular velocity. 55 degrees over 4 days. 13.8. You got all that nonsense? All right. We want to take the average angular velocity. So on the next page, we're not going to do spot C because we're already taking a lot of time as it is. We need the average angular velocity. That's the average of 12.3 and 13.8. 12.3 plus 13.8 divided by 2 is 13.1 degrees per day. Let's remember the formula that we derived before. The period, which turns out to be something called the synodic period, is 360 degrees divided by the average angular velocity, which I called omega. This is omega. Okay, so it's 360 degrees over 13.1 degrees per day. Let's punch that up into our calculator. 360 divided by 13.1 27.5 days. It's days because the degrees on top cancels the degrees on bottom, and 1 over 1 over days gives you days. This is not the true rotational period of the sun. Okay, here's a confusing part. As Earth is tracking the sunspot, Earth is not stationary, but Earth is also moving around the sun. For instance, in 6 days, we might have observed the sunspot being there, but 6 days later, the Earth measures the sunspot over there. The 27.5 days is the synodic period. It's the time for a sunspot to match up to a moving Earth. We, however, want the sidereal period, which is the time for the sunspot to go around the sun with respect to the distant stars. I'll skip you the geometry lesson for now, but let us say that one can calculate the sidereal period from the following formula. It's the sidereal period is 365.25 days times the synodic period over 365.25 days plus the synodic period. But we've got to put that part in parentheses. Our synodic period is 27.5 days. So let's plug that in both spots. 365.25 times the synodic period, 27.5, divided by, open parentheses, 365.25 plus the synodic period of 27.5. Close parentheses equals 25.6 days. Well, we should probably only round this to 2 significant figures because of those 2 significant figures. So we round ours to 26 days. I was hoping we'd end up with 25, but you know, we're close enough. And that is how you calculate the rotation rate of the sun. So please turn in this page, and whatever your tracing paper jobby is over here. If you can scan that too, that would be nice, or photograph it. And that is how we calculate the rotation of the sun. Once again, there's the front page. There's the back page. And there's the tracing paper. Okay. I guess I'll stop the recording there.